So the next section we're going to cover is the law of cosines. And this is also used to solve triangles, but more specifically, it's going to be used when we don't have a full pair of information. So I don't know alpha and A, I don't know beta and B, I don't know gamma and C. And I have no way of getting a full pair easily either. Like in the case of angle, side, angle, you have two angles, you can find the third, so it's not difficult to then get a full pair. Here, there's going to be no way, because if I have side, angle, side, I have no information connecting a full pair. And there's no way to figure out what these two angles are if I only know one. So this is really good when we know all three sides, or again, we have the side angle side case, so no full pair. So what I want to do is I want to build the formula just by doing one of the cases, and then we'll show you just the law of cosines in general. So the same idea is going to hold that we've done before to prove most of these things. We don't know about just any triangle, but we do know about right triangles. So I'm going to go ahead and I'm going to drop a perpendicular line down to side C, and I'm going to call this side H. And it's called the law of cosines, so I want to deal with cosines. So when I talk about these angles, I'm going to need the adjacent sides here. So I know this total distance is C, but I don't know what these smaller portions are. So I'm going to call this portion over here X, which means if I want this piece, X plus this has to add up to C. So this side would be C minus whatever X is, okay? So this makes two triangles, call them triangle 1 and triangle 2. I have the left half and then I have that right half, okay? So I have two right triangles. Here is one, and then here is the other, okay? They both have this side as that height. The bottom here is X, the bottom over here is C minus X. This is my right angle. This is side B, this is side A, this is angle alpha, and this is angle beta, okay? So I'm gonna look at cosine of each of these angles. So for triangle 1, cosine of alpha is the adjacent side over the hypotenuse. And then for here, cosine of beta is the adjacent side over the hypotenuse. Sorry, that should be A, okay? So I have both of these pieces. This, however, not so nice. So I'm not going to worry about this one because C minus X looks like it's going to be disgusting. So this is going to be a nice way for me to be able to solve for X. So looking at these two, this one is way better. So X is equal to B cosine of alpha, okay? Then the other thing I can do for each of these triangles is I can use my Pythagorean theorem, because my whole goal is I want to get a relationship between A, B, C, and then one of these angles. I don't want to use H or X. I want to be based on the given components of my triangle. So I have a way to rewrite X in terms of two pieces of my triangle. Now what I want to do is I want to see, can I rewrite H to be able to get rid of that as well, okay? So from this first triangle, using my Pythagorean theorem, let's move these over a little bit, is if I take one side squared, add the other side squared, it equals the hypotenuse squared, okay? And then over here, I've got one side squared plus the other leg squared is equal to the hypotenuse squared, okay? So what I'm going to do in both of these is they both involve an H squared. I'm going to rearrange it and solve for H because then those things should be equal. So from here, H squared is going to be B squared minus X squared, okay? And then over here, H squared is equal to A squared minus C minus X squared, okay? And then because these both are H squared and they are both this distance here, these two things better equal each other. So what we get is that B squared minus X squared needs to equal a squared minus c minus x squared, okay? So this is fantastic because now only I involve this unknown x, but I have a way to rewrite x. So mostly from here, I'm going to do some algebra, and then we'll go ahead and plug in what x needs to be, because it's easier to work with x than it is that expression. So over here, we're going to FOIL this out. If we FOIL that out, we get c squared minus 2xc plus x squared. Then distributing that minus sign gives us a squared minus c squared minus 2xc minus x squared. And that actually turns into a plus because I forgot to distribute that minus to everything. Now, in this case, if I went and added the x squared, something nice happens. Those two cancel each other out. So that tells us b squared is equal to a squared minus c squared plus 2xc. And then I'm going to go ahead and I'm going to rearrange this some more, and I'm going to solve for a squared. So b squared plus c squared minus 2xc will equal a squared, okay? And then I don't like the a squared over there. Let's solve that on its own. So just flip the order of these two. And then we'll go ahead and plug in what x is going to be. So x, remember, is 2b cosine of alpha. So this is 2bc times cosine of alpha. Okay. So this gives me a relationship between all three sides and one angle, okay? So if I know two sides and an angle, then I can figure out the third side from here. Or if I know all three sides, A, B, and C, my only thing unknown is the angle. So then I can go ahead and solve for that. And then again, you can do an analogous proof of these just by dropping the perpendicular in a different spot, but the same idea holds. So if you notice over here, you have a squared, and over here you have alpha, and then this involves the other two variables. So that formula is going to be really easy to adapt based on the information you have. So in any triangle, these three relationships hold. A squared is equal to b squared plus c squared. You can kind of think of it like the Pythagorean theorem, but since it's not a right triangle, we have to subtract 2bc times cosine of alpha. So again, these two correspond to exactly what you add here, and then the one on the left-hand side matches the angle that you have. So instead, if I put side B over here, my two other sides are A and C. So those go in those places. And then the angle associated with B would be beta. And then finally, if I have C squared, A and B are the other two sides. And then the angle associated with C would be gamma. So it's all going to depend on the information that's given to you, which of these formulas you would go ahead and use, whether you use the law of sines, whether you use the law of cosines. But again, this one works really well when you don't have a full pair. The one piece of advice I can give you, though, is that if you start using the law of cosines, it might seem really natural that you now have a full pair once you figure out one of the missing pieces to then use the law of sines. But remember, with the law of sines, there's ambiguity. So if you start using the law of cosines, keep using the law of cosines. Don't switch it up, okay? If you start using law of sines, then continue using with that. Because again, this formula is definitely messier and harder to work with. So if the law of sines is what is appropriate to start the problem with, do that. But again, if you have to use the law of cosines, keep using the law of cosines. You won't introduce any ambiguity. And with the cosine inverse function, that one's much nicer because quadrant 1 is positive for cosine and quadrant 2 is negative. So there's going to be no ambiguity when you take that inverse cosine on anything. You will find the correct angle. You will never have to search for an extra triangle or if a triangle exists or not. Okay? So let's try a few examples of this. We're going to solve the triangle if it exists. So we're given alpha, b, and c. So as you can see, we don't have a full pair of information. But I'm going to go ahead and still draw my triangle. Alpha pairs with A, beta pairs with B, and gamma pairs with C. The info that's given is B, C, and then the angle between them. So this is that side angle side case. And again, I have absolutely no full pair, so I cannot use the law of sines. So since I do know alpha, we can go ahead and we can use the law of cosines to find the side across from it. So we're going to go ahead and we're going to find side A. Okay. So I want A. That's going to go off on its own. The other two sides get added over here. We subtract 2 times their product, and then we times that by the cosine of the angle between them. So A squared is on its own, which is nice. B is 15, C is 24, and then we have 2 times 15 times 24, and then alpha is going to be 86 degrees, okay? So for this one, I'm going to trust you can plug this into your calculator. You should get that this is about 750.775, okay? And then to get A, you want to take a square root. So A is about equal to the square root of 750.775. So side A is going to be about 27.4, okay? So that is our one missing leg. Okay. So again, we now have this. I need to find my 2 remaining angles. You can pick whichever one you want, but as soon as you have one, then you can use the fact that the 3 of these have to add up to 180 degrees. So I'm going to go ahead and I'm going to find beta first. So we'll go ahead and set this up. But again, I do not want to use the law of sines. Even though I have A and alpha, I don't want there to be ambiguity because this could give me the wrong inverse sine value. So I want to stick to using cosines. So I need to match beta, which means B is going to go on its own. So then we have A squared plus C squared minus 2AC, and then times cosine of beta. You're not going to be able to avoid using unrounded values, even if you did do that bad decision of switching to the law of sines, because you have to use A to find beta. So plugging in B is 15, A is 27.4, C is going to be 24, and then we have 2 times 27.4 times 24, and then we have cosine of beta, that is our unknown. Okay. So 15 squared would give us 225, and then I'm going to avoid my calculator right now, but I'll at least switch over when I have to find this. I'm going to go ahead, if you add those 2 things together, you should see you get 1,326.72. And then 2 times 27.4 times 24 will give you 1,315.2. And then that's times cosine of beta. From here, we then need to go ahead and solve for cosine of beta. So I'm going to start by moving this to the other side just by subtraction. And at that point, again, we need to use a calculator for this. So that would give us negative 1,101.72 is equal to negative 1,305.2 times cosine of beta. And then at this stage, when we divide by this quantity, thankfully the nice thing that happens is those minus minus cancels, and you go ahead and turn to positive. So when I divide through, I get 1001.72 divided by 1315.2, and that's equal to cosine of beta. So to get beta on its own, we take inverse cosine, which again is arc cosine or cosine to the -1. Your calculator usually has cosine to the -1 because it takes up less space. And so this would be the value of beta. So again, just to show you, I'm going to plug this into the calculator to at least give you that example. But at this stage, you should be pretty fluent with using that button on your calculator. But I'll bring up Desmos to show you. So you should have a function that looks like this on your calculator, or again, if you just use Desmos, it is cosine to the -1. That's the same thing. You want to make sure you are in degree mode because when we're working with triangles, degrees makes more sense. So we take 1101.72 and we need to divide that by 1315.2. And that gives us a rough approximation for our angle, but beta is going to be about equal to 33.1 degrees. Okay. All right, so let's go ahead and go back into here now. We now have beta as well, so the only thing missing to find is gamma. And in this case, again, we just use the fact that the three angles have to add up to 180 degrees. So gamma is 180 minus alpha minus beta. Alpha was given to us. So just going back up here, alpha is 86 degrees. And then beta we just figured out is 33.1 degrees. So gamma, again, going to be an approximation. It's about equal to 60.9 degrees. Okay. And again, this makes sense for our triangle because if you go back and look, we've got alpha as the biggest side or biggest angle. So A should be the biggest side, but gamma is pretty close. So A and C are pretty close in size. Beta is the smallest angle, so B is the smallest side. Okay, so that is everything that we have or need to find. So let's do one more example of these. We're told a triangular plot of land has sides A equals 217 feet, B is 362, and C is 345. We want to find the measure of all three angles. So again, we have the three sides. We do not have a full pair. So we are going to use the law of cosines. Okay, so I'm given what side A, B, and C are. Okay, so this is that side case. So we're going to use the law of cosines. We're going to use this to find the first two angles. And then the third, we just use the fact that they need to add up to 180. I again do not want to switch to find this. In the case that you really hate this so much that you need or feel the need to use the law of sines, to show you here, A is 217, B is 362, and C is 345. You have to use the law of cosines at least once. What you would do is you would find that biggest angle. So 362 is the biggest side. That tells me beta should be the biggest angle. If I find that, then there's not going to be ambiguity when I go to use the law of sines, because this is the only angle that can possibly be obtuse. And that's what's going on when we're dealing with that other angle in quadrant 2. You're finding an obtuse angle with the law of sines. So if you go that route, then you'd be able to see or make sure there's no ambiguity. Okay. So we need to go ahead and we are going to use the law of cosines to find two angles. We'll start with alpha, since that's the first letter. So our law of cosines tells us a squared is equal to b squared plus c squared minus 2bc times cosine of alpha. Okay. You can absolutely fill in all these numbers and work piece by piece, or you can also go ahead and solve for cosine of alpha first, then plug in all your numbers. So just to get some practice manipulating this, let's go ahead and let's add this to the other side, and then we'll subtract a squared. So moving that over gives us 2bc times cosine of alpha is equal to b squared plus c squared minus a squared. And then dividing through by bc, cosine of alpha is all of this stuff over here divided by 2bc. Then we go ahead and we're going to take cosine inverse of this expression on the right. And then at this stage, now I have everything for alpha. We go ahead and plug all these side lengths in. B is 362. C is 345. And A is 217. So we need to subtract that. And then we divide this by 2bc. And then we plug that into our calculator. So again, I think you'd be okay doing this. You should get that your alpha is going to be about equal to 35.6 degrees. I like doing this better where I solve for alpha first, because if I had to plug these numbers in and then I'd have to manipulate it, they're going to be some big numbers, okay? So we have alpha. Now let's go ahead and solve for beta. And we're really going to do exactly the same thing. Honestly, you can just take this formula and swap those roles of A and B. So really, without doing any work, beta would be A squared, this would be B squared, and then that would turn to an A. Your roles of A and B switch. But just to show you, since we're finding beta, that means B squared is on one side. The other two sides are A and C. And then we times that by cosine of beta. And again, doing the same rearrangement, we go ahead and add this to the other side, and then we subtract B squared. So it swaps the two places of these things. And then we go ahead and divide by 2AC. And then we take cosine inverse. So again, could have gotten that directly from here. Your B swaps to an A in both of those spots, and then A swaps to B, and this swaps to beta. So filling in those numbers, B is going to be our cosine, A is going to be 217, C is 345, and then B is 362. And that's over 2 times 217 times 345. So if you were to plug that into your calculator, you should get that beta is about equal to 76.5 degrees. Okay. Now that I have two of the angles, I'm just missing one more. So that's the last angle we need to find, which is gamma. But again, I know gamma, alpha, and beta have to add up to 180. So gamma's approximately 180 minus 35.6 minus 76.5. So our third and final angle is about equal to 67.9 degrees. Okay. All right, so that is our law of cosines. The last thing we're going to do is kind of like we did with the law of sines, how we had another formula to find the area. We have another formula to do that here, which is called Heron's formula. So if a triangle has side lengths A, B, and C with a semi-perimeter, remember the perimeter is just the sum of everything. So if you have a side or triangle, that is not a triangle. You have a triangle with A, B, and C. The perimeter is the sum of those. The semi-perimeter is denoted with an S. It is half of that. Okay. Then the area of our triangle is given by the following formula. Okay. You can take the square root of the semi-perimeter times S minus A. So the semi-perimeter minus A, the semi-perimeter minus B, the semi-perimeter minus C. Okay. I definitely do not have the time to go through the proof of this formula. That would take way too long. So instead, what I'm going to do is I'm going to find the area of the triangle two ways. We're going to do it using this formula, and then we'll do it without, because we're going to know what the base and the height of this triangle are. So starting out to use a Heron's formula, the first thing I need to do is find the semi-perimeter. iPad's jumping around. So it is 1/2 of the perimeter, which is 20 plus 20 plus 32. So adding those together gives us 1/2. 20 and 20 is 40, plus 70 plus 32 is 72. Our semi-perimeter is 36. So our area is going to be a giant square root. Probably going to need more than that. We take the semi-perimeter, then the semi-perimeter minus one side, semi-perimeter minus another side, semi-perimeter minus another side, which is 32. Okay. So here, it does happen to work out nicely for this example. 36 minus 20 is 16. Then we get another 16, and then we get a 4. And these are all perfect squares, and they're being multiplied, so you can take the square root of each. Square root of 36 is 6. Square root of 16 is 4, another 4, and then square root of 4 is 2. So if you go ahead and multiply all of these out, you should get 192. So that is our area. But again, I definitely don't need to use Heron's formula. This is just for this specific example to show you this formula does work. Remember, our area of a triangle is 1/2 the base times the height, and the base and the height are the two things that form the right angle. So in this case, our base is 32, and our height is 12. So that's going to give us 1/2 times 32, which is 16, times 12, which is still 192. And that's really the same thing here, because 6 times 2 is 12, and then 4 times 4 is 16. So you end up with exactly the same result, okay? So again, you're going to need to be able to distinguish which of the different cases you're in, whether you need to use law of cosines or use law of sines. If you're given a full piece of information or can quickly find a full piece of information, then you're typically going to use the law of sines. However, if you don't have a full piece and there's no way to easily come about that because you're given two sides, not two angles, you need to go through and you need to use the law of cosines. And again, I'd recommend sticking with the law of cosines.